All right, well, thanks, Klaus, for that introduction, and thanks you all for calling in this evening to hear this talk about NASA's DART mission. And so this is something I'm very excited about, and I hope you'll leave this talk with hopefully some enthusiasm for the project as well, and actually ways that you might be able to get involved with the mission, or at least interact on a very detailed way with how this experiment is going to unfold. So for those who have not heard about DART, DART is the Double Asteroid Redirection Test. This is a NASA mission that's being led out of APL at Johns Hopkins University, the Applied Physics Laboratory. And there are many, many aspects to the DART mission, and I'm not going to have time to talk about all of them, but I'm really going to be focusing in on how ground-based observations are absolutely essential and built into the framework of this mission, more so than any other mission that I think has come before it. It really is kind of unique in the sense that ground-based observations from the telescopes that we have at Lowell and elsewhere are essential to the success of the mission. So I'm going to be talking about DART. I'll give a bit of an overview about, what is this experiment that we're carrying out, and what is it that we hope to accomplish. I'll talk about some of the details of that and the problems that we're trying to solve right now. I'll then discuss what we know about the target body of this mission. It's an asteroid known as Didymos. And I'll talk about all the work that has gone into understanding Didymos before the spacecraft is even launched. And then at the end, I'll talk about the sort of culmination of the mission, the end of life of the mission, and what that means for ground-based observers to help solve the problems that have been laid out ahead of time. So let me start with a very high-level overview here of the NASA Planetary Defense Coordination Office, or the PDCO. This is a relatively new office or department within NASA. It was only established about 5 years ago in 2016. And the PDCO is tasked with a number of activities, and that's sort of summarized in this planetary defense diagram. And so kind of going through this briefly, can you see my cursor? Can you guys all see my cursor?
Yes.
Okay, great. If we start kind of in the upper right-hand corner here, the PDCO, or the planetary defense activities at NASA, are tasked with searching for, detecting, and tracking near-Earth asteroids or hazardous asteroids that could potentially impact the Earth. And there are a variety of assets involved in doing that. There are efforts to characterize these objects, so not just finding them, but understanding what they are. And this is a lot of the work that I do, is trying to characterize newly discovered near-Earth asteroids that have been discovered by NASA's search facilities. A lot of this characterization and tracking and searching is compiled by the IAU's Minor Planet Center, which is housed at Harvard, as well as tracked by the Center for Near-Earth Object Studies at JPL, where they assess the hazard of all these objects that have been discovered. And so the IAU Minor Planet Center kind of keeps track of the catalog, and JPL kind of assesses what hazards may exist in that catalog based on probability of impact. And that's what this is all about, is understanding which objects in the near-Earth asteroid catalog are dangerous, have a non-zero probability of impacting, and what we should do about them. Now, on the bottom left-hand corner is sort of some of the activities related to what we might do if we do find something on an impacting trajectory. And there are almost political aspects of that, planning and coordinating responses through various working groups, not just at NASA, but international working groups that have direct connections to the UN. So if tomorrow a 200-meter asteroid were discovered that's going to impact over a populated area, these working groups or these advisory groups would get fired up and be the sort of conduit for communication between us scientists that are behind the eyepiece of the telescopes and the policymakers that may have to make tough decisions about what to do about an impacting body. And then the last slice of this is mitigation. So if something's found, what do we do about it? How do we mitigate that threat? And to date, really, all the mitigation activities have been exercises, sort of thought experiments about, what would we do if, and then talking through that thought experiment about which government agencies would get involved, organizations like FEMA and things like that. And so, at least giving thought to this beforehand, so we're not caught unprepared for potential significant disaster. But you might notice also in this mitigate section here is DART. And so this is that Double Asteroid Redirect Test. And so this is NASA's first planetary defense exercise or experiment. I think it's safe to say it's the world's first demonstration of planetary defense capabilities. And so it's interesting for a lot of perspectives. Now, the planetary defense aspect of all of this is very important. It's what motivates a lot of this, but there's also some fantastic science that comes out of carrying out an experiment like DART. And hopefully by the end of this, I'll convince you, that it's not all about sort of the grand idea of saving humanity and saving the planet, but it also does some really cool things for understanding formation and evolution of planetary bodies in the solar system. So DART, which is shown over here on the left, and Hera, shown over here on the right, are sort of a tandem set of missions that form what is been given the acronym, yet another acronym, called AIDA. And so AIDA is the Asteroid Impact and Deflection Assessment. And so NASA is running DART and is planning to intercept this asteroid Didymos, which I'll be talking about in just a second here, in 2022. Hera is a European mission that is planning to then rendezvous with the Didymos system in 2026. So NASA will carry out the sort of intercept part of this experiment, and I'll talk about what intercept means. And then Hera, or the European Space Agency, will carry out the sort of detailed characterization of that system after NASA's done its thing. So there's a pair of missions, both going to the same object and all focused on understanding Didymos from the perspective of a sort of planetary defense angle. I should have said at the beginning, I will just keep on talking unless anybody interrupts me. So feel free to jump in if you have questions, or if anything I say goes by too quickly or anything like that. I'm happy to pause and clarify any points if I say anything that's unclear.
Okay, I'll jump in here.
Sure. Yeah,
how much warning? Okay, this intercept, this has been the one on the left, the NASA one, that's been launched already?
It has not been launched, and I think that's a great precursor to the next slide. And so here's the overview of DART.
I was just going to ask how long what's the warning period?
Yeah, so I
imagine it varies.
Yeah, so we have different concepts, and there really are all concepts at this point for planetary defense options. And the parameter space is in terms of which option you might be required, is almost entirely dictated by the size of the body and how much warning time you have. So large bodies with small warning time are really hard to deflect, and you start getting into only options like thermonuclear standoff blasts. If you have a small body and lots of lead time, years, decades, then you have a lot more options, things like gravity tractors or a kinetic impactor, which is what DART is. And I'm going to talk about that here in just a second. So there are different sort of concepts, as I say, on the table. None of them have been tested. And so DART, as I said, is really the first of these sort of demonstration experiments to show if we can really do this or not, if we had to. But DART would be applicable to sort of the kinetic impactor deflection scenario where you have years or decades of warning time. As for how much we will get, we don't know. I mean, we had the Chelyabinsk impactor over Russia in 2013. And so that was only a 20-meter sized body, and we had no warning on that. It just happened. One of the reasons we didn't see it coming is that it was a relatively small body, only 20 meters or so in size. And it was coming at us from the direction of the sun. So our telescopes are not good at searching in the sun for asteroids. And so we just didn't see it coming. And so Chelyabinsk impacted over Russia. It damaged a bunch of buildings. About 1,500 people ended up going to the hospital. So it was a significant event. It was one of the largest impacts of the past century. And so these things will happen. It's inevitable that we'll get another one. We don't really know when, and we don't really know how big of an object. Generally speaking, we should get more warning time for big objects just because they are easier to detect with our telescopes. But this is a complicated problem, and our completeness, how many objects we've discovered in different size ranges, is wildly incomplete in the sense that we know that there's a lot more objects out there than we have yet to discover. So we have a lot of work on the discovery game to build that census of the near-Earth asteroid population to know that we're able to actually track all the objects that could pose a hazard.
Are there any plans to send up satellites that are similar to Rubin on Earth and whatnot, with high H10 to be able to scan towards the sun?
Absolutely. Yeah, absolutely. And there's several some are on paper concepts, some actually have hardware in the lab. The most likely to fly in the near future is a thermal infrared surveyor called NEO-SM, surveyor mission, and it's an infrared optimized wide field survey that's going to scan the sky looking for these objects, and it's actually highly complementary to Vera Rubin because of, first of all, the fact that it's operating a different wavelength regime, but also it's able to access viewing geometries that Vera Rubin will not be able to access. So when you combine Vera Rubin and NEO-SM into sort of a cumulative survey, we can actually meet some of the US congressionally mandated goals for NASA to detect X percentage of all the dangerous asteroids that are out there in near space. So the current congressional mandate is we were supposed to have discovered 90% of all the 140-meter bodies or larger by 2020. And so we have not done that. NASA was not essentially funded at a level to be able to achieve that goal. So we've not achieved our congressional objective or our congressional mandate.
And how would you know that? Even if,
Sure. Yeah, and that's a great question, and it's probably a whole other talk just to describe that in detail. But the bottom line is you can look at discovery rates at different size regimes, and you can look at how they trend over time. And you can also look at redetection rates of objects to get a sense of, how likely it is that we're missing objects within a given size bin and how many more out there. And then you tie it all to population models and try to come up with an estimate of what our completeness rate is at these different size regimes. And if I'm remembering the numbers off the top of my head correctly, I think we're at something like 10% completeness at 140 meters. And as you go smaller down to 20 meters, we're at like 1% completeness or something like that. So for every one 20-meter NEO that we know out there, there's hundreds more out that have yet to be discovered. So completeness drops off pretty steeply.
Nick, does that mean only the ones that are visible to us, not the ones that are coming at us from the solar side?
That's right. I mean, yeah. So these population, essentially what people do is they take the discovered populations, the ones that have been found by these discovery surveys like Pan-STARRS in Hawaii and the Catalina Sky Survey in Tucson. They're constantly discovering new objects at historic rates. We're discovering over 100, 200 NEOs every month. Wow. And so we take those discovery rates and build up the catalog of known objects and then use that known population to infer what we think the underlying true debiased population is. And so it's model based, but the models all seem to tie together pretty well, so, at the order of magnitude level. Okay, so DART. This is the overview, the high level overview of DART. And so, as I said, DART is going to the asteroid Didymos. And Didymos, let me go back. Didymos is a binary asteroid. And that's really one of the special things about the Didymos system that enables this experiment. About 15% of near-Earth asteroids are binaries. So Didymos is kind of rare in that regard. The primary, or the larger body in the system, Didymos, is about 780 meters across. Separated from it by a distance of about 1 kilometer is Dimorphos, which is its satellite. Dimorphos is about 160 meters, and Dimorphos is in orbit around Didymos. DART is going to be targeting the Didymos system, DART will launch sometime in late 2021. This got pushed a little bit by COVID slowdowns, but those have not affected the mission at all. The mission will still be able to proceed as planned. So launch is late 2021, maybe pushing into 2022. And then it's a pretty short cruise phase where this spacecraft has got one destination. It is going to go straight for Dimorphos and smack into it at something like 15,000 miles per hour. Just before that impact, it drops off a little CubeSat known as LICIACube. It's an Italian-built CubeSat. And that CubeSat is going to trail behind the main spacecraft and image the damage or the effect of this DART spacecraft smacking into Dimorphos. So we launch late this year, a little over a year from now, we hit Dimorphos. And from basic momentum conservation, we expect the Dimorphos orbit period around Didymos to change. And that's the experiment, that's everything. Hit a spacecraft into a satellite of an asteroid and look at how its orbit period changes. Now, because DART obviously is lost in this experiment, we have no spacecraft to do those measurements. And LICIACube is not designed necessarily to measure that change in orbital period. So that's where Earth-based observations come in. We have to use Earth-based telescopes to measure that change in the orbit period of Dimorphos around Didymos. And so it's kind of an interesting approach where you have the spacecraft serving as, a massive body smacking into an asteroid, and then looking at what happened from that, rock hammer experiment with telescopes down on the Earth. The timing of this impact is around September 30th of next year. It could be October 1st. There's some wiggle room there in terms of exactly when it's going to happen, but it's around the end of September, early October next year. And that corresponds to a time when Didymos is actually quite close to the Earth. It's only going to be 0.07 AU away from the Earth. So relatively close. It's going to be near perihelion for Didymos. So it's not only close to the Earth, but it's close to its near sun approach. And that means it's actually going to be quite bright. And I'll talk about what quite bright means at the end of this presentation, where there'll be some very interesting observing opportunities of Didymos before the impact, during the impact, and following the impact to characterize what happened with this experiment. Now, in terms of top-level requirements for DART, this is sort of restating some of the things that were on the previous slide, but it's good to kind of explicitly spell these out. So step one, we want to impact Dimorphos. And we're going to do that during its close approach to the Earth when it's nice and bright and easily observable with ground-based telescopes. And that's in the sort of September, October timeframe of 2022. The spec for the mission, or the requirement for the mission, is that the orbital period of Dimorphos around Didymos is changed by at least 73 seconds. We don't know exactly how much the period is going to change, and that's one of the reasons for doing this experiment. But the baseline requirement is 73 seconds.
What is the current period?
I'll show that in just another slide here. The current orbital period of Dimorphos is 11.92 hours. So it's a relatively small change. This is, as I say, the baseline. Models suggest we could have several minutes of period change, but it's not, Dimorphos is an interesting size object. It's 150, 160 meters across. So in terms of likelihood of impactors that are dangerous, this is sort of the sweet spot in the undiscovered space of near-Earth asteroids. So it's an interesting experiment from the practical aspect of trying to deflect an object that's overlaps closely with hazardous bodies. But the size of the spacecraft compared to a 160-meter object it's a big size ratio. I don't know what the actual number is, but the spacecraft is tiny. It's not, compared to a 160-meter body, it's not going to have a dramatic, it's not going to disrupt the body. It's, a little bit more than a fly on a windshield kind of thing. So we're not going to be changing that orbital period by hours. It's going to go from 11.92 hours to 11.92001 hours or something like that. So it's going to be a small change.
Nick, if I can ask, that all this is based on a combination, basically, I guess, of Newtonian physics, right? One mass bangs into another mass. Do you
That's
know?
right.
Do you know the actual mass of the little satellite?
No, we don't. And I'll talk about that in just a little bit here. I think the next slide actually is going to address exactly that and why it's not quite as simple as just basic momentum conservation. Because if it was, we could do the experiment on paper and be done.
Gotcha.
So we change the orbital period of the satellite. We then measure that period from the ground, and we do that to within 10% accuracy, or 7.3 seconds. I think we could probably do better than that, but we measure that change in the orbital period, and that then allows us to look at what's known as a beta factor. And I'm going to talk about that in some more detail in the next couple slides. And beta is what we refer to as the momentum enhancement factor, because it's not just the momentum of the spacecraft. We know the mass, we know the velocity of the spacecraft quite well, so we know that momentum in very high precision. It's not just that momentum being imparted to the satellite. And it's because of this beta factor, which has to do with the way impact ejecta is removed from the surface of the body when you hit it. And so beta is a momentum enhancement that you get from ejecta leaving the surface of the body. So let me show that in a really cool movie on this next slide here. And I hope this shows up. This is one of the things I was worried about with bandwidth issues. But what you're looking at here is a real world, sort of miniature DART experiment where we have a 1 meter granite sphere being hit by a 4 centimeter aluminum sphere that's been fired at 2 kilometers per second. So of course the sizes and the size ratios and the velocities are not a great match to DART, but it's order of magnitude, right? And the thing you notice here is that when this video is slowed down, of course, I don't know what the frame rate here is, but it's incredibly slowed down, that you have a lot of material leaving to the left of frame, right? Which is where the impactor came from. And it's this impact ejecta that enhances the momentum delivered to the body in ways that are really hard to predict. For this particular experiment, beta, this momentum enhancement factor, is 2, which means that if you took just the momentum of the particle, this 4 centimeter aluminum sphere, you'd have to multiply that by 2 to figure out how much momentum was imparted to the granite sphere. So you can get significant enhancement due to this ejecta ejection off the backside of the body. And that's really important for sort of planetary defense aspects, because we want to know how effective a kinetic impactor is going to be if we have to move an asteroid a certain amount in its orbit. So measuring beta really is the crux of this mission. And here's sort of the equation of what beta looks like. It's essentially the ratio of the imparted momentum over the momentum of the spacecraft. So how much enhancement you get beyond just that of the spacecraft. So if the imparted momentum is just equal to that of the spacecraft, beta is 1 and you don't get any momentum enhancement. But with this extra ejecta carrying momentum off in the backwards direction, you get a momentum enhancement, and you can get values between 1 and 3. Again, we don't really know what's going to happen because we don't understand the surfaces and internal structures of asteroids very well. Our observations generally probe just the outer layers of asteroids, and so we don't really know what's under the surface. And so when I said earlier, this is kind of like a rock hammer experiment, it really is breaking down the body under the surface and using that experiment to hopefully figure out a little bit about what the structure of these things are that might help inform some of these planetary defense strategies. Okay, and so here's this is all theoretical or experimental in the sense we've set up granite balls in the lab and shot bullets at them to see what happens. This is the sort of theoretical side of things where if you have different structures, you can get different beta values. And so here are 3 models that show an asteroid with no porosity, so just a whole bunch of particles that are in tight packing to one another. An asteroid that might have microporosity, so you might have some void spaces between the particles, think sort of grains of sand on a beach kind of thing, where you can compact the sand down because there's pore space between the grains of sand. Or you can have a rubble pile where you have a size distribution of particles with a few big ones and lots of small ones. And in these models, you are essentially impacting from above and looking at what happens to the ejecta and how that then translates into different beta values. And in particular, how you get different velocity changes for, in this case, the simulated Dimorphos. And so you can get different velocity changes in the orbit of Dimorphos around Didymos depending on what the surface and subsurface structure of the body is. And again, we have no idea what that is. And so that's really the point of doing this experiment, is what is the geologic nature of the surface of Dimorphos, and what does that mean for planetary defense applications? So beta is critical. What is that enhancement value, and what can we expect for it if we need to design a kinetic impactor mission for real? Okay, so that's sort of the overview of DART. The bottom line is we're going to smack an asteroid with a spacecraft and look at what happens. But we need to understand the Didymos Dimorphos system in great detail before we change it, right? We can't just do the experiment and then look at what happens if we don't know the detailed state of the object beforehand. The experiment would be a failure. So most of what I'm going to be talking about here is setting that baseline of what we know about Didymos and Dimorphos before we actually hit it with the spacecraft. And of course, the exciting part of all this is what happens next year when the asteroid actually gets impacted by the spacecraft. And then we get to look at the before and after. Okay, so here is a cartoon. It's not a cartoon, it's an animation with some real data in it of a different binary system, but there's some striking similarities to Didymos, and so it's applicable here. So as I said, Didymos is a binary. About 15% of NEOs are binary, but it's a special binary in the sense that it's eclipsing. So our line of sight from Earth for significant portions of its orbit is along the orbit plane of the binary system. So that means we see mutual events, eclipses and occultations of the primary by the secondary and of the secondary by the primary. And so as the secondary, the satellite, is going around the primary, we see it occult and eclipse the primary. And that manifests as brightness changes, just like you would see for any eclipsing or occulting object in the sky. That manifests as brightness changes as observed from Earth. And so this unique geometry allows us to characterize, through detection of these mutual events, the orbit period of Dimorphos. If Didymos and Dimorphos were not in this favorable geometry, we would not be able to do this experiment. But it's because they are in this alignment where we can see these mutual events, these dips in brightness when, for example, Dimorphos passes behind Didymos, as you would see here coming up right there. Dimorphos disappears, brightness would drop because the total area of reflected light going back to Earth would decrease. You also can get drops in brightness when a shadow passes across the primary, for example, like you saw there. As Dimorphos comes around, it can cast a shadow on the primary, attenuating some of the light that's getting scattered back to the observer. So it's this unique geometry that makes this whole experiment possible. Prior to 2015, which is really when I started getting heavily involved in this, this is more or less what we knew about the Didymos system. And this is a complicated slide, and I'm going to walk through this in some detail because I want to reference back to similar slides like this downstream in the talk. So Didymos was found to be a binary asteroid in 2003 and really was not observed in any great detail following that until 2015. So pretty much everything we knew about Didymos until 2015 was based on these 2003 data from Petr Pravec and colleagues in 2006 paper. And as I indicated on that previous slide, when we go and measure a brightness variation or light curve of Didymos, it's really a combination or superposition of several different things. You have the rotation of the primary that's causing brightness fluctuations over time. You have the rotation of the secondary, which is causing brightness fluctuation. And then you have these mutual events, these eclipses and occultations that are causing the brightness to dip over time. And so this measured light curve, which is the top panel here, has all of these phenomena sort of superimposed on one another. And you get what kind of looks like a messy jumble of stuff. And so the game we play is all about decomposing this into the constituent parts so that we can understand what the primary rotation is, what the secondary rotation is, what the timing of those mutual events are, and thus what the orbit period of the satellite is. And so these are what are known as phase folded light curves. And so the top two here are folded to the orbit period of the satellite of 11.9 hours. So these are phase folded, which just means that if I were to go out and collect, say, 24 hours of data, if I were to somehow point a telescope at Didymos for 24 hours, the first 11.9 hours would get plotted from 0 to 1 in orbital phase. And then the next 11.9 hours would get plotted on top of that, going from 0 to 1. So you're looking at sort of folding the data onto itself at a specified period. And that helps build up signal to noise and enhance the strength of detection of events of interest. And so the top two here are folded to that orbit period. And when we do that, we get the measured data here. And when we do the decomposition, decomposing this light curve into its constituent parts, we have a very nice mutual event light curve here that shows that at orbit phases, 50% out of phase from one another, you're seeing primary and secondary mutual events, these dips in brightness due to the secondary passing in front of or behind the primary. And we also get a primary rotation out of all of this. This is part of the decomposition, and we get a primary rotation period of 2.26 hours. So again, all of this dates back to sort of 2003 observations. Didymos was in a very favorable apparition then, much brighter than it has been for many, many years. I believe these observations were carried out when it was around 12th magnitude. So it was a very favorable target for getting these high quality light curves and characterizing the system. And so you would look at this and you'd say, okay, well, back in 2003, we knew the orbital period, we knew the rotation period. It seems like we're set up for carrying out the DART experiment. Well, not so fast, because it turns out things get complicated. And that is due to a radiative phenomenon known as the YORP effect. So I'm going to talk about this here and describe why it's not enough just to say we knew what the system was like in 2003. And so we can now carry out our experiment to see what happens when the DART impacts. So the YORP effect is named after a number of investigators here, some of whom worked on some of the concepts of this phenomenon dating back to the 19th century. So it's the Yarkovsky, O'Keefe, Radzievsky, Paddock effect, the YORP effect. And so the basic idea of YORP is that sunlight can cause rotation periods to change, for an asteroid rotation periods to change. And so the way this works is you have incident sunlight coming in, shown by these yellow arrows here in the bottom. So incident sunlight hitting our spherical cow, which is meant to represent an asteroid. That incident sunlight is going to heat the surface, and boulders on the surface, which might be represented by these wedge-shaped things here on the sides, the wings, boulders on the surface will re-radiate that incident sunlight as thermal photons. This is a phenomenon attributed to thermal inertia. This is why when you go put your hand on the sidewalk in the afternoon, it's warm, because the sidewalk's warming up. It's a rock effectively, and it's re-radiating those thermal photons. So incident sunlight warms up the surface. Those re-radiated thermal photons are emitted normal to the surface. But because asteroids are irregular, right? They're not spherical cows, but have lumpy surfaces. Those thermal photons are re-radiated not in parallel directions, but in a random collection of directions due to the detailed topography of the asteroid. So what that means is you get a non-zero torque. These objects, due to these thermal photons carrying away very small amounts of a momentum, will cause a net torque on the asteroid, which can cause it to either spin up or spin down. So its rotation period can change as these thermal photons escape. And so that means you have an effect here, a radiative pressure effect or a radiative effect that is causing asteroid spin rate states to change. So asteroids don't stay with constant spin states, but actually change over time. So that is the YORP effect. There's a bonus aside here on the binary YORP effect. And it's conceptually the same, it just applies to a binary system where you have incident sunlight heating this binary system. And this is actually a real shape model of Didymos. We don't really know what Dimorphos looks like. It's just an ellipsoid in this image, but you have your incident sunlight heating the surface, thermal photons being re-radiated in non-parallel directions. You get a non-zero torque on the system where essentially the secondary serves as a lever arm on that as a way to torque the system. And that can actually change the binary orbit over time. So the binary orbit period is going to change over time due to this binary YORP effect. Okay, so we have this radiative pressure effect that not only can change spin states, but also can change binary orbits. And that's now starting to get messy because we are very interested in knowing what the orbit period of Dimorphos is around Didymos. And if the sun is messing things up, then that could complicate the success of this mission. So the binary Yorp effect was only first predicted in 2005. This is not something we've been thinking about for decades. It's a fairly new phenomenon that when Didymos was discovered to be binary, we weren't even thinking about binary Yorp. Really, as I say, it was not until 2005 that the theory for this was written down. Binary Yorp is yet to be observationally confirmed. We have yet to see a satellite around a primary slow down or speed up due to this effect. There have been null detections where we have data of sufficient quality that we can say that this satellite is not evolving under any binary Yorp. But we've yet to have a positive detection one way or another for any binary asteroid. And that's interesting for lots of reasons that we don't really know why that's the case. But this last set of bullets here is the important part. So what is the magnitude of the binary Yorp effect? Well, photons don't carry a lot of momentum. And so we're talking about something like 1 to 10 centimeters per year in the semi-major axis drift of the satellite around the primary. So the satellite's the semi-major axis of that orbit of the satellite around the primary. It's going to drift by 1 to 10 centimeters per year, which translates to an orbit period drift of 1 to 10 seconds per year. So that means at the upper end of this sort of range of possible values, since discovery, the Dimorphos orbit period could have changed by up to 200 seconds. Now that's a pretty high upper limit. I wouldn't have expected it to change that much, but that's a potential problem because we have data in 2003 that found that orbit period of Dimorphos to 11.92 hours. But Yorp could be comparable in magnitude to the effect that we expect from the DART impact. So we have the impact that's going to impart a period change again of hopefully 70 seconds or so or more. And we have this natural phenomenon of Yorp that can change these orbital periods by potentially a similar magnitude. So that means we can't just stop in 2003 and say we're done with Didymos. We need to keep observing it to understand whether or not it's evolving under this binary Yorp phenomenon. So I'm going to show a table here of date, telescope, magnitude, and RMS residuals of Didymos observations. And so these are all those 2003 observations. As I said, it was favorably bright, 12th magnitude. So that's not a incredibly challenging target. Getting residuals this low is challenging. But these are those characterization data that I showed at the beginning. Now, Didymos was not really favorably observable until 2015. And so it was in 2015 that we started doing a lot of observing because we knew we had hoped in 2015 that DART was happening, finally got approved. And so we just kept on observing. And the goal here really is to understand how the system's been evolving over time. And so the Didymos was observable in 2015, 2017, 2019, and then again, just a few months ago at the end of 2020 and early 2021. We've used big telescopes since 2003 because the V magnitude shown here in this column of Didymos has been challenging to work with. 20.6 magnitude, 21, 19, high 19s, high and mid 19s. And we've continued trying to collect very high quality data using some pretty big apertures. There's some Keck data in here using a 10-meter telescope, the GTC, the 10.4-meter telescope in the Canary Islands. Magellan, 6-meter in Chile, Gemini North in Hawaii, an 8-meter, and then a lot of DCT, which was the Discovery Channel telescope and has since been rebranded as the Lowell Discovery Telescope, has been used continuously throughout this process. And actually, Lowell has been a major contributor to understanding Didymos since 2015. If we look at the highlighted rows here, these are all the DCT, LDT observations that we've carried out. We could not have done this on a smaller aperture where we're really pushing DCT to its limits, or LDT to its limits, which is great, being able to leverage an asset in that way. But if we look at the number of mutual events that have been detected since 2015, 17 out of the 24 that have been used by the mission have actually been detected from LDT. So we've made a major contribution to understanding the system over the past 5-6 years. So Didymos at the Lowell Discovery Telescope. Objectives kind of harkens back to sort of the top level requirements of the mission. We want to refine the Didymos spin period. We want to determine the system geometry in detail. So where is the spin and orbit poles of these systems? And we wanted to characterize that BYORP, the binary YORP evolution of the system. So we want to determine in detail what is the dimorphos orbit period, not just in 2003, not just in 2015, but in particular in 2022, right before we actually hit it with the DART spacecraft. So again, I don't know how well this movie's showing up, but this is one of the nights of LDT data from, I guess, January 14th. We've over the past 5.5 years, we've spent 10 nights at LDT observing Didymos, which is not a huge number of nights, but having that sustained access to LDT has really been a critical part of the success in this experiment. And we've been using our large monolithic imager. There's a 12 arc-minute square field of view, 0.12 arc-seconds per pixel, some other vital stats there on this image sequence. For those that maybe have not spotted the asteroid yet, put a little ellipse on it. So it's this relatively bright object moving through the center of the frame here. So it was a very nice night. It was one of the better nights we had at LDT. This is what a 19.5 magnitude object looks like with 180-second exposures or so at the LDT. So these are the data that we've collected to generate light curves and look at that photometric variation of Didymos over time. And so here's just one example of the recent data that we've collected. And this is a similar plot as to what I showed before, where we've got the measured light curve at the top. Again, the measured is a combination of the primary rotation and the mutual events. We then decompose it to look at the mutual events, and then we get the primary rotation as well. And so this is from one night in January 14th, where we have LDT data and a little bit of Keck data that got thrown in as well. And that turned out to be quite valuable because Keck is farther west than us, so they could observe at times that LDT could not. And that turned out to be quite valuable because what we can see here in this light curve, in the decomposed mutual event light curve, is we actually see a primary occultation, a primary eclipse, and then the Keck data picked up a secondary occultation. So it's pretty cool that we're able to see such incredible detail in the light curve. And it's a testament to the quality of the optics at LDT, as well as Keck, of course, but it helps having 10 meters of aperture to be able to get good quality photometry. So this is kind of characteristic of the data that we've been collecting over the past few years. You know, we're aiming for really high precision photometry to look at these brightness variations and really characterize the timing of these mutual events to be able to tease out the orbital period of the satellite. So in terms of pre-launch objectives, coming back to those, we now have a pretty darn good constraint on the rotation period of Didymos. And that's largely for just sort of contextual purposes. It's not critical to the success of the mission, other than it'd be nice to know what it is as we're flying by, what the rotation period Didymos is in the system. We've determined in impressive detail what the system geometry is. And so what is the orbit plane of the system? And that's what this polar projection is showing, where prior to 2019, I believe, the dashed region here, which may or may not be showing up too well, the dashed region was the range of possible solutions. And now with the addition of data in 2020 and 2021, we've pinned down the pole position of the orbit plane to an uncertainty region of only a few degrees across. So we know in exquisite detail what the orbit plane of the satellite is, of Dimorphos is around Didymos. And so that last objective was determine the Dimorphos orbit period and the binary YORP solution. Let me talk a little bit more about that. So at the end of 2019, that observing season there, we still had 3 possible binary YORP solutions. And those resulted in 3 sigma uncertainty on the position of Dimorphos at the time of impact. And that 3 sigma uncertainty was plus or minus 65 degrees. So that means we knew where Dimorphos would be in 2022 in its orbit. to an uncertainty of 65 degrees, which was outside of spec. The mission requirement said that we need to know where Dimorphos is at the time of impact within plus or minus 45 degrees. And a lot of this uncertainty is due to these three different binary YORP solutions that were all consistent with the data through 2019. And I don't want to get into this in too much detail other than saying we have sort of three versions of binary YORP drift, where the object could be essentially 0 centimeters per year change in the semi-major axis, 1 centimeter, minus 1 centimeter per year, or plus 1 centimeter per year. So these are the three solutions we had going into the 2020-2021 observing season. And each of those correspond to a different orbital period of the satellite. So really what we were trying to do is eliminate two of these three solutions. So we collected lots of data. Again, we're kind of showing primary rotation and mutual events. And so this is data from December, January, February, March, lots of data. The bottom line is that we were able to refine the orbit period of Dimorphos around Didymos to 11.921626 plus or minus lots of zeros, 18 hours, which is 65 millisecond error on that orbit period, which is just a staggering number to think about, that we know the orbit period of Dimorphos to that level of precision, which translates now to an uncertainty of only 10 degrees in Dimorphos's position in its orbit at the time of DART impact. So we've far exceeded the mission requirement of a 45-degree uncertainty. We know pretty much exactly where Dimorphos is going to be, which is very helpful to the spacecraft to be able to hit the target in the first place. And interestingly, we don't fully understand why this is the case, but the data are consistent with a zero BORP evolution. And this could be related in some way to the way energy is exchanged within the system. Certainly the sunlight is acting on Dimorphos and can cause its orbit period to change, but there are other ways that energy can be exchanged between the primary and the secondary. For example, tidal effects can cause energy exchange. And so those could be working to counteract any BORP spin up or slow down, but essentially our data are consistent with a zero BORP solution. So this is just coming back to those pre-launch objectives. We've refined the Didymos spin period. We defined the system geometry. We now know Dimorphos's orbit period and where Dimorphos is going to be at the time of DART impact to quite high accuracy that will enable this experiment to take place. So we think we understand the Didymos Dimorphos system now, thanks to a lot of nights spent at the telescope and some careful analysis done by a number of folks. Now the whole thing starts over because we're going to change the system. We're going to change everything when DART impacts. And so we have to start over, meaning we have to now remeasure everything that we just spent all these years measuring. And this is when things start to get kind of interesting in terms of the observational campaign required to carry this out. And so this is the sort of schematic of this concept where you have the original orbit that we now know to exquisite detail, the orbit period of Dimorphos around Didymos. DART is going to smack Dimorphos around September 30th. That's going to put it onto a new orbit. And we want to be able to measure that new orbit based on these mutual event timings. So again, we're starting over with a sort of fresh set of observations to characterize the system after the impact next year. So let's look a little bit at observability here. And I'm gonna do the risky thing of trying to show a live demo in the middle of a talk. But hopefully this goes off without too much of a hitch. So for those that don't know, Lowell maintains a website that is located at asteroid.lowell.edu. Can everybody see this web browser?
Yep.
Yes.
Okay, great. So for those that don't know, this is a website, is one of the other projects that I work on that's related to asteroids, but not necessarily DART specific. It's sort of more about the population. The landing page for asteroid.lowell looks like this, and you can see in the solar system visualizer here, essentially dots representing asteroids. We can search for individual objects. And so if I search for Didymos here, it's going to pull up the information we know about Didymos and plot it in this diagram, where Didymos has a semi-major axis of 1.6 AU. If I scroll over here a little bit, we can see perihelion for Didymos, shown by this blue dot, is essentially right at Earth, and that's when the DART impact is going to happen next year. If I scroll out, move out along these axes, we can see aphelion is out here in the main asteroid belt, out past 2 AU, and then the current position of Didymos is right here. So Didymos is almost at aphelion and will be coming in leading up to the DART impact at perihelion next year. Now, the reason I wanted to show this site, there's a lot of cool functions in here that we use and others in the community use for observing asteroids. And so if you're interested in asteroid observations, check out some of the tools here. The one that I'm going to pull up is something we call ASTOBS, or asteroid observations. And so this is an observation chart builder where you can pull up information about the observability of an object based on input parameters. And so I'm going to adjust some of these input parameters. So we're interested in observations dated around sort of late summer, early fall next year. I'm going to look at the observability for 1 year. And let's say this is where we apply filters to observability. Let's say we can observe down to, I don't know, 18th magnitude, let's say. Something like that. We're interested, say, in solar elongation, so the angle away from the sun of 90 degrees or more. We're interested in declinations, maybe suitable to Arizona of, I don't know, minus 20 degrees. And we don't want to observe in the galactic plane, so we'll avoid things that are 20 degrees outside of the plane. So those are our filters we're going to apply to the data. And now we've got a box down here to Didymos. Oops. There we go. And so this kind of works like a shopping cart. I'm going to add that asteroid to my shopping cart. And we've got plots generated now to look at the observability of Didymos from July 2022 through July 2023. And so impact is going to be around here, late September in 2022. And we're looking at different parameters that can influence how observable something is. So here we can see in late September, early October, in this plot window here, that we're looking at V magnitudes of about 14.5. So not quite as good as it was in 2003, but pretty good. We've got galactic latitudes that are, declinations that are pretty low, right around impact, minus 30 degrees, but rapidly climbing through October into November, so that it's at positive declinations and much more observable. And what is shown here in the windows in the bottom is essentially all the times when the criteria that we've set up over here on the left, when those criteria are met. So these are your observing windows, when you could take your telescope and point it at Didymos to observe. You can play around with these filters and that will change the observing windows. So that is gives you a sense of sort of the observability of Didymos next year. 14.5 magnitude is a highly accessible target. It's one of the reasons that the impact date is set as around this time, because that means ground-based telescopes are going to be able to actually get high quality data of the object right around the impact. So let me go back to the presentation here. So this is just summarizing what I just said. So for several months, August through November next year, it's going to be brighter than 16th magnitude. At impact, it's going to be about 14.5 magnitude. And again, the high quality photometry will be needed to detect these mutual events and remeasure the orbit period. But now we're doing it through a dust plume. And that's one of the things that makes this interesting. And so this is where we get into completely theoretical sort of cartoon level understanding of what may happen following the impact. This is adapted from a preliminary model from one of the mission investigators, Jin-Young Lee at PSI. And so here we're looking at plume brightness following impact as a function of time. And so we think there'll be sort of a multi-stage brightening where impact happens over the period of several hours. The object's going to ramp up in brightness, or the plume is going to ramp up in brightness as material escapes the secondary. It'll then slowly fade as that sort of ejecta evolves outwards, and then even more slowly fade over the course of many weeks or months. We have no idea what the peak brightness of this plume is going to be, and that's really one of the points of doing the experiment is what is this plume going to look like? How bright is it going to get? But models suggest it could be in the range of 10 to 12 magnitude, something like that. So it could be significantly brighter than Didymos itself. So you may get significant brightening in this object, which is going to make it potentially a very interesting show to watch as this impact takes place. Oops. Go back. Thought I had one more transition in there. I guess not. What was I going to say? Yeah, I guess the point I was going to make here is that we don't really know how bright it's going to get, but things that are in the 10th to say 14th magnitude range means we can't be using telescopes like Keck or Gemini or Magellan to observe because those will saturate. That you can't get good quality data on really large telescopes. We're going to have to rely on 1 meter class telescopes. We're going to have to rely on smaller telescopes to actually do the characterization we need to understand how the system reacts to the DART experiment. So just kind of coming to a close here, returning to these top level requirements of sort of, what's going to happen with this mission. We're going to impact Dimorphos. We're going to change the orbit period. We're going to measure that period change and use that to infer what beta is for this system following this experiment. And so at impact, Didymos will be 14th magnitude and the plume may get up to 10th or 12th magnitude. So 1 meter class telescopes will be essential in the months surrounding impact. And so just as a summary here, I showed you sort of 5 years of a campaign focused on Didymos from LDT specifically that now reveal Didymos spin period and pole, the Dimorphos orbit period, and a constraint on the zero Bjork evolution of the system, which we're still trying to understand. We're looking forward to launch of the DART spacecraft later this year with impact a little over a year from now. And so the path to beta continues in 2022 when we sort of start all the observing over again. And we'll need to measure that new orbit period of Dimorphos and figure out what happens when you smack a spacecraft into an asteroid. So that is all that I've got. And so I'll be happy to take any additional questions if there are any. I know we're kind of getting up on the hour here. I don't know how hard of a cutoff you guys have, but again,
we don't. Boy, okay. What an exciting experiment. That is really interesting. I have a theoretical question. Like, let's say sometime down the line, we discover another binary pair that is a threat potentially to actually hit us. And we want to send out some sledgehammer to change the orbital parameters. Which one would one aim for, the satellite or the primary? And what effect would that have?
It's a great question, and I'm not sure I have a great answer for that. There are people that are modeling what the heliocentric change in orbit will be for the Didymos system following the DART impact, and it's going to be even smaller, right? It's the change. Yeah. It's essentially going to be dictated by how much ejecta escapes the system, as opposed to settling back down on the secondary or the primary. It's potentially detectable with the right instruments, and maybe by the time Hera gets there 4 years later, we may be able to detect that, but that's really small. So if I had to guess, a kinetic impactor is maybe not your optimal tool for a binary asteroid deflection. I know people have looked at the nuclear blast option, which is not something, that should not be option one, but there could be scenarios where it's the only option. And if you detonate, so the way the nuclear standoff works is you detonate off the surface of the object. So you're not actually hitting the object with the nuke, but you're actually detonating some distance off the surface. I don't know what that optimal distance is. And what happens is you essentially vaporize material on the surface from that standoff blast. And that vaporization acts as a jet, so that material's vaporizing and blasting off the surface of the asteroid, and that causes them to sort of get pushed. So if you had your nuclear standoff happen between the two objects, if you were able to somehow get your blast positioned halfway between the two or something like that, you could have a cumulative effect that could, I don't know if you could split the objects, but you could certainly push them both in hopefully complementary ways. I don't know.
Yeah.
But
Well,
I think
it wouldn't take much, would it? I mean, to change orbit?
well,
Much of a
it all
push?
depends on how much time you have. We're talking about these, and DART's a small spacecraft, right? It's a 600 kilo spacecraft. That's not a big spacecraft at all.
No,
It's relatively small, but we are limited by how much mass we can actually send up. So to get enough deflection, you'd probably, if it's a big body, you probably need a fleet of spacecraft, and you get far more complicated there. And the deflections we're getting off of DART are, we're talking centimeters per year kind of thing,
Yeah,
right?
yeah.
And so that doesn't help when the Earth is thousands of kilometers across.
Right.
You need a lot more deflection than that. And so people think about this, and people are working on this, and this is step one. This is literally dipping our toes in that pond,
Right,
and
right.
seeing what happens with a kinetic impact. And we'll see, maybe some of the early theories of what would happen if you hit an asteroid with a kinetic impactor suggested it might be like a bullet in a pillow effect, where you have, the bullet just kind of poof and nothing happens, right?
Nothing
It just
happens,
kind of
right.
sinks in and nothing happens, which would be informative, certainly. We don't think that's going to happen for a variety of reasons, but it's a pretty unconstrained problem at this point, and that's
Yeah,
what makes it so interesting.
Absolutely, yeah.
What technology is used to hit the asteroid? Is it like your radar, thermal?
Yeah, so that's I'm not entirely up to date with that, but it's really a good part of DART is tech demo, right? I mean, it's a tech demonstration mission, right? We're actually not a science mission at all. We're an investigation, and a lot of that involves new tech, from the thrusters that are being used to the guidance and the onboard imaging. So it is an imaging system. It's a high-speed imaging system that is interfaced with the thrusters. So it will be self-targeting. And there's some sequence of events there where X number of days out, ground-based control is entirely hands-off, and the spacecraft takes care of it from there, which is amazing. And I think they can hit to some incredibly high precision on the surface to within tens of meters or something like that. So it's amazing that this can work, and that there's all kinds of complications because you have two bodies that are rotating, and you've got shadowing and all kinds of stuff. And so there's detailed models being developed to try to address exactly these issues. But it's real-time processing of images, trying to identify limbs, and limbs as in the terminators on surfaces, and using that to infer the size of the body and where the spacecraft could best hit. I don't know how much the impacting software will try to do beyond just hit the center of brightness or hit where we think the center of the body is. But you could imagine a very different outcome if you were to hit a pond of small grains, like a sand pool, versus if you were to hit a boulder, right? A large boulder on the surface. You could have very different outcomes, and we may get some information about that. The last image before impact may be insightful. The Leisha CubeSat is going to provide some insight on that, but it's not clear the dust plume will clear out before Leisha Cube flies by. And so that's really where the Hera, the European component of this, comes in. Hera is going to arrive 4 years later, and will characterize in detail the impact crater that DART made, and answer a lot of the open questions related to how much mass was actually removed from the surface of Dimorphos. Did any of that mass settle back down onto Dimorphos or Didymos and things like that?
So now you selected a binary asteroid because it gives you the best data. You won't actually be able to tell whether you've changed the path of it, correct?
Okay, so the reason we chose the binary, I had zero say in any of this. The reason a binary was chosen is because it has these mutual events that we can use as a clock for what the orbit period of the satellite is. So because that clock exists, that makes this experiment possible. So that's the reason the binary was chosen. And it also means that we're not trying to deflect a kilometer scale body, which would be even harder to detect. We're only deflecting 160 meter size body, which is a little bit easier to detect. But the actual deflection of the system, the heliocentric deflection of the system in its orbit is going to be incredibly small. As I indicated, there may be a possibility of detecting that over a long enough time frame. You may see its orbit around the sun change at an incredibly low level, but that depends on what happens to the ejecta. If none of the ejecta leaves the system, then its orbit around the sun is not going to change. If lots of the ejecta leaves the system, then yes, its orbit may change, but people have just started looking at that, and that's not a top level objective at all for the mission. If we're successful in detecting a change in the primary or the secondary orbit period, that's going to provide a lot of information about how effective this kinetic impactor may be.
One science fiction like scenario I remember reading about is that if you detect the potential threat early enough, that I think one of the ideas was to actually land a lander on the asteroid and then have it have a secondary engine that could ignite and slowly push it out of the way. Is that still a viable model? As opposed to blowing it up.
These are all concepts at this stage, and I don't know if we have enough information to know whether any of these are good ideas or bad ideas. There are alternative models that may be slightly more favorable related to that, particularly the idea of a gravity tractor. So you take a massive spacecraft, park it X number of kilometers off the surface of the asteroid, and have it slowly thrust away. And so the mass of the spacecraft will attract the asteroid, and it can, without ever having to touch the surface, it can slowly pull it away from its orbit over time. And that takes a long time, depending on the mass of the spacecraft and things like that. The benefit there is you don't have to worry about trying to anchor into an unknown surface, which is, we don't know what these surfaces are like, and whether you even could take, I don't know, grappling hooks and hook onto the surface and then have a thruster push on it. We just don't know if that would even work. So the gravity tractor is a similar, sort of thruster-based design that could work over long periods of time, but doesn't require you mating with the surface. There's all kinds of crazy ideas out there. Ideas of you could put a rover on the surface with paintbrushes or spray paint and paint the surface so it would be optimized for radiation pressure, so that it could act like a solar sail. So that the sun could, the influence of the sun on the orbit, the influence of the sun and the solar radiation pressure could change the orbit faster than it would ordinarily. So there's crazy ideas like that if you painted the surface. Lasers, of course, are involved. You have to get lasers in the game, where you could have high-powered lasers fired at the object, maybe targeting a specific area. And so you're vaporizing material, and that material jets out, and you've created a little jet engine. If you keep targeting that same area over and over and over again, you get a sustained push. So there's lots of possibilities. And
well, that's why your experiment is so important as a first step, isn't it?
Yeah, and it's really fun, right? I mean, who doesn't want to who doesn't want to do something like this? So yeah, it's a lot of fun, and it is an important first step because it'll provide some insight into what these unknowns are.
It appeals to the kid in us because you're just smashing things together, but you get all kinds of neat data.
Yeah, exactly. Yeah, absolutely. I mean, it's just fun. It's a fun experiment to do. And the thing that gets me so excited about the mission is how integrated the ground-based observations are. I mean, I'm a telescope user, and I love using these telescopes for interesting observations. And this is a mission that absolutely requires the ground-based telescopes, and in particular the optical telescopes, to understand what happens. So that's very exciting.
Yeah. Certainly see that.
I have a question. Are these very clean systems? Like there's no other debris swarming around the major components?
Yeah, it's a great question. I think the short answer is we don't know. and I can provide a little bit more information about why we don't know. So NASA recently had the OSIRIS-REx spacecraft leave the asteroid Bennu. And so this is a sample return mission where the OSIRIS-REx spacecraft touched down on the surface of Bennu, picked up some material, and is bringing it home. When OSIRIS-REx got to Bennu, it discovered that Bennu is shedding material. And we still don't fully understand why an asteroid would be shedding material in the way that Bennu is. It looks like mass ejection events, kind of like a comet, but Bennu is an asteroid, and it could be thermally related, so that rocks get heated up on the surface and thermally crack. And when they crack, they sort of slough off dust and particles off into space, but we don't really know. And so we got to Bennu, and there's stuff around Bennu that wasn't expected to be there when the mission was conceived, and even when the mission was launched. It was an entirely new discovery to find mass ejection events on an asteroid like Bennu. So, you know, in Bennu's case, that could be compositionally driven. It could be just thermal physics. We don't know, but there could be stuff around Didymos that surprises us in the sense that, okay, there's maybe material there that we had not predicted to be there from the beginning. The other thing that is related to this is how we think these binary systems formed. If you looked at some of those images of Didymos, it's a top-shaped, what we call a top-shaped object, where it has an equatorial ridge aligned with sort of, you know, the spin pole of Didymos. And we think what has happened for systems like that, and we see these top-shaped morphologies all over the place. We think what has happened is that Didymos was once spinning faster than it is now, maybe due to the Orp effect. And as it was spinning faster, material slumped down from the poles, collected at the equator, and if you get to a critical spin rate for a particulate body, it can actually shoot material off of the surface. And the satellite, Dimorphos, may have formed through this sort of spin up and rotational instability process. Now, we have models that predict that. We've never really seen that happen in real time, but that could be a messy process where you're not just kicking off Dimorphos, but maybe other material as well. So there very well could be other things in the Didymos system that we just have not detected because they're too faint or too small or whatever. So we don't know. The proximity approach will potentially provide some of that information. There are limits, pretty good limits on how big particles could be in that system. And I think that those best constraints probably come from the Arecibo radar data of Didymos, where Arecibo was able to observe Didymos, characterize the shape of the primary, detect the secondary. And I think they probably would have found stuff down to meters in scale, maybe 10 meters in size, if it was present between Dimorphos and Didymos, and they didn't see anything. So there's not any big stuff that has yet to be detected, but that doesn't mean there couldn't be small stuff.
Is it fair to say that really there's a wide spectrum of compositional characteristics of asteroids, everything from puffballs to solid rocks kind of thing?
Oh, absolutely.
What would have caused that initially in the protoplanetary nebula?
Right. So the range of compositions is huge amongst asteroids, and the way we infer that is through meteorites. So these are pieces of asteroids that have made their way to the ground. And when you look at our meteorite collections, there's a wide diversity of mineral types and compositions and thermal histories and aqueous alteration states and all kinds of things. So it's a fascinating array of stuff. In some cases, minerals that we just don't see on Earth all that frequently. Right. And that, of course, is a filtered population. The meteorites are, in the sense that only the strongest meteorites are going to survive to the ground. And that if you're a fragile, friable rock that has low cohesive strength, you're not going to survive a passage through the atmosphere. You'll just vaporize in the atmosphere. So we have a biased sample in terms of meteorites that land on the ground. And so there's almost certainly more fragile things out there than we have here on the ground. OSIRIS-REx has provided some interesting insight on that, where the indications are that you have things that look like boulders on the surfaces of these asteroids, but they're very low cohesive strength. They're very high porosity. So it's not a boulder in the sense of what we think of here on Earth. They're large, coherent structures, but they may be kind of like sandcastle, dried out sandcastles kind of thing,
Yeah.
where if you know, it can maintain a structure, but a little tap and the whole thing falls apart. We just don't know. So you have a wide variety of compositions, a wide variety of structures, almost certainly physical structures of these rocks. There has to be the sort of, you know, coherent rocks because we have the meteorites, but then we also have evidence from some of these space missions that the rocks may not all be coherent blocks, that they could be more fractal in nature. As for what that means for the formation, one of the great things about near-Earth asteroids is that they are geologically a really short-lived population. If you're a near-Earth asteroid, because you're coming in close contact with planets, Earth, Mars, Venus, because you're coming in close contact with those planets, you don't survive very long. The planets win those gravitational tug of wars, and these objects get kicked out of the solar system into the sun. Out, you know, they get scattered. So a typical near-Earth asteroid will have a lifetime of 1 million years, a few million years, 10 million years, something like that. So that means near-Earth asteroids are constantly being replenished, and so there are reservoirs from where that replenishment is happening, and the main belt is one of them, but there are also cometary reservoirs and other things. So when we go to near-Earth asteroids, we're going to things that are really close to the Earth, but they're coming from all over the solar system, and we're able to sample distant reaches of the solar system and study distant reaches of the solar system that we ordinarily would not be able to study. So what that means is we're sampling different formation environments, things that may be formed out past the snow line, out past Jupiter, things that formed close into the sun, where the Earth formed, things like that. And those formation environments would have differed in their chemistry and their temperatures and the physical conditions that these objects experienced 4.5 billion years ago as they were coalescing into solid bodies. So near-Earth asteroids give us a window into all these different things that allow us to better understand those formation processes.
Wow, interesting.
Are we making any headway in determining the G magnitudes of some of these asteroids?
G magnitudes, the apparent magnitude, like the Gaia G, is that what you're referring to?
No, I mean the albedos of these asteroids.
Oh, the
optical
albedos.
searches, which is just assumed to be 0.15 for pretty much everything until measured.
Gotcha. Gotcha. HG. Right. Are we making headway? Yeah. Yes. There's an active mission, still an active mission called NEOWISE that's flying right now. And NEOWISE used to be known as the WISE satellite, and it's an infrared satellite, sort of a precursor to this NEO-SM mission that I mentioned previously. That's going to be this all-sky thermal infrared asteroid optimized discovery tool that would complement Vera Rubin. So WISE and NEOWISE really were kind of, WISE was conceived as a cosmology experiment. And then the asteroid people realized it could do asteroid stuff and kind of co-opted the mission and took it over. And some of the more interesting discoveries from NEOWISE or from WISE have been solar system related and not so much cosmology. But NEOWISE is still plugging along. It's been going, it's many years past end of date, expected end of date. So it just keeps going, it won't die. And it keeps providing data. And one of the things NEOWISE is doing is it's operating in the near infrared or in the mid infrared, the thermal infrared. And so it's able to directly measure the sizes and albedos, or it's able to directly measure the diameters of asteroids. And so when you couple that with a visual apparent magnitude, you can get at what the albedo is for these objects. And NEOWISE has observed hundreds of thousands of asteroids, mostly in the main belt, but also some near-Earth asteroids as well. And so that, you know, just the sheer statistics of that has certainly improved our understanding of these sort of HG values and things like that. But there are definite limitations, and it's not unusual for us to go and target an asteroid that, say, the Minor Planet Center is predicting to be some magnitude, and it turns out to be half a magnitude off one way or another. And that's because we don't have good calibrated understandings of that phase, the HG phase relationship. There's always room to improve that. I think Vera Rubin will definitely contribute to that, but it's not the kind of thing that's going to happen overnight. It's the kind of thing where 5 years into the survey, you'll start to have enough data to be able to, you'll start to have enough repeat observations of individual objects to be able to refine their HG values. So we'll get there for sure. And we certainly have far better understanding than we did even just say 5-10 years ago. Part of that's just driven by large data that has come in from projects like NEOWISE and others. But there's always more work to be done.
So we lost ranging with Arecibo. Is there any plans to replace that with anything? And how much of an impact is that going to have on this kind of a mission?
Yeah, and that's a tragic loss. It's really sad to see that happen. So we do have other facilities that can provide some of that capability. And for DART, the Goldstone array is going to provide some of that observational capability. Maybe in I don't know the details of the plans at Goldstone for that. For the mission, but it's possible Goldstone could operate in a bistatic mode so that it maybe transmits and then you have Green Bank, for example, receiving or something like that. So that allows you to get higher resolutions and things like that. So we will have Goldstone operational and helping out with the mission. So that will pick up some of what Arecibo would have been able to do. I think what it means for the mission is it puts a higher emphasis on the optical facilities, your visible wavelength facilities to carry out the experiment to make sure that we get the measurements needed to confirm whether the experiment was successful or not. So that's good for those of us that use optical telescopes, but it's still quite sad to see Arecibo go. There was a second half to your question. I forget what that was. I'm sorry. Or maybe I answered it. I don't know.
Yeah.
Kind of did with the Goldstone. I was asking what the impact was going to be on these kinds of missions, and you said we have Goldstone and we can bounce it off Green Bank and whatnot. So some of it can be recovered.
Yeah, I mean, yeah, you kind of asked, what are the plans for that for Arecibo? There are discussions going to build Arecibo version 2, these are, when you're talking about a facility of that scale, this is not something just one organization is going to get involved with. It's a massive billion-dollar project, and so this becomes decadal survey territory. So what is the strategic priority of the astronomy community as a whole? And so the planning and discussions for that have started, and with decadal surveys soon, to the planetary decadal survey soon evolving quickly, the hope is that there will be an emphasis within that document highlighting the need for something like Arecibo, because we would love to see it come something like that come back. Whether it's 1 kilometer dish in the mountain in Puerto Rico, or whether it's something else, I think is to be determined and to be discussed. There's definitely a niche for a facility like that, or the capabilities that a facility like that can deliver, and we'd love to see that niche filled. But exactly what and when Arecibo 2.0 happens is a ways off, certainly, and will be a point of discussion for many years.
Meantime, of course, China has a giant equivalent, doesn't it? Can you get them
That's right,
involved, or is that online yet?
It is online, but it's difficult for political reasons to work. Work internationally across. There's international restrictions, explicit restrictions in place that forbid us from working directly with Chinese on missions like this.
Does that transmit enough power to be able to use?
I don't know the details. It's certainly it's the world's largest radar dish now. I don't know what its power specs are.
Maybe what's needed is an international thing like the 30-meter telescope or some equivalent, and have other countries, participate. I
think that would probably be needed to build something that's to redo Arecibo in some way.
Yeah.
There'll be debate about whether it should go in Puerto Rico or somewhere else. One of the big things that's not talked about a lot with the loss of Arecibo is what that meant to the sort of infrastructure of Puerto Rico, where you have universities training students as engineers and scientists to use that facility and support that facility, and that has gone away entirely now. And so it's a hard hit for for the island, and the sort of future scientists that were growing up looking to get involved with projects, maybe not directly with Arecibo, but at least learning how to run a facility like that and then take that experience elsewhere. So it's a really sad aspect of the loss of the facility, independent of the scientific loss. There's an educational component that's tied into the education of those students at the universities and schools on the island.
I have a question. Would you be able to look back in hindsight, and I know the mission isn't even over, but to talk about hindsight, but could an argument be made that it might have been better to do the impact when the object was further out and fainter, and thus more suitable for large telescopes to observe?
That's a good question. I think.
Would you rather a night's data with the LDT or 20 bits of data cobbled together from 1 meter telescopes?
Well, so the mission will be contracting facilities to carry out the observations. That's what they did with LDT. So I've been working with the mission as a co-investigator to carry out these LDT observations. And we had to do that because the object was 19th magnitude. There's no way to get that level of precision at a smaller facility. And so the mission will adopt a similar approach, and discussions are happening now of what that plan will look like. What suite of telescopes, what fleet of telescopes do we want to point to the object? And I think the main benefit there is, I can get, for the past 5 years, I've gotten a total of 10 good nights of data at LDT. Well, I can get 10 nights on a 1 meter this month if I need, right? Like I don't need 5 years to spread that out. And so the sheer accessibility of 1 and 2 meter, 1 meter class telescopes is hugely in our favor. In the sense that we can get a lot of nights on those facilities, and there's a lot more of those facilities out there that I think outweighs the benefits of going to a larger aperture. The challenge becomes more than training the observers and training the facilities so that they can make sure to deliver data of sufficient quality. The data that were obtained in 2003 clearly show, those were on 1/2 and 1 meter class telescopes. You can do it. You can deliver the data of the quality the mission needs with those small facilities, but you have to have the experience and the tools to be able to do it.
I had a question, Nick. The comment was, I think the FAST telescope, the Chinese radio telescope, doesn't have a transmitter. In fact, it would have to be redesigned, I think, pretty heavily. So the Goldstone solar system radar is the only place now, after Arecibo is gone, that has a good radar. I think they're also planning to try to develop one with a Green Bank telescope, but I don't think it's operational yet. They're just using it, like you said, for bistatic purposes. But the question I had was about the beta value that this mission, as I seem to be saying, is one of the primary goals to determine. And that's sort of that. Yes, it's pretty interesting to know it for this object, but how valuable is it for every other object, when the sense is that, it's going to depend on the object, on the type of object, and the maybe even object-object density variations and things like that. So does this in a way have to be determined anew for every object, or is at least the hope that for every type of object, every classification, every certain classification, you can just keep using this once you determine it? Or how good is that for future use?
Yeah. Give me just a second. My headphones are running out of battery, so I'm going to unplug them and switch over to my speakers and computer. I heard all that question, but before I answer, let me switch over to the speakers and get my headphones out. Can you still hear me?
Yep.
Okay. Yes, we would love to run DART for every possible asteroid that exists out there, and hit boulders and hit sand ponds and hit every composition and hit comets and all that stuff. And the reality is that we can only do one of these experiments now, but it'll be a data point, and we'll have that data point and work with it for years, and then we'll want to collect other data points. So you're absolutely right, though, that it's just one part of this huge parameter space, and the hope is that we would collect enough data before we actually have to do this for real. Maybe sample a few different types of objects before we have to do this experiment for real, so that we have an informed, are better informed than just going into it blind. On some level, it's not. This is outside my area of expertise, so I maybe shouldn't even add this caveat. But on some level, it may not matter when you're talking about 15,000 mile per hour impacts onto a surface. It may not matter compositionally whether that surface is 10% iron or 20% iron or carbonaceous chondrite or ordinary chondrite. It just that's such high speed that a rock's a rock, and detailed differences in composition may not matter all that much. But I don't think we know. I don't think we have enough information really at this point to know for sure.
Along the lines of a second question I was thinking of asking is, sorry, I maybe should have prefaced this by saying, Brent Arkinol, I actually worked for USGS Astrogeology. So I did a paper at the 2013 Planetary Defense Conference about characterizing asteroids close up from nearby spacecraft flybys and orbits. And but one of the things I questioned then, there wasn't really an answer for, was what about topography? What, if you hit at a certain angle, even if it's a spherical object, if you hit it at an angle, it's going to be different than if you hit it head on. So as you alluded to earlier, if you hit a boulder or you hit a mountain or you hit the slope, what's the difference? And you're right, maybe in the other point you made, it doesn't matter if you're going 15 kilometers a second, you're still going to do a lot. But what if it did? What if it's a glancing blow? What if there's a change? So one of the things that I sort of propose is certainly on these objects where you have several years notice, you almost need, if possible, to have a reconnaissance mission to collect this kind of data, to actually measure the topography, maybe have a projectile impact to measure the density and the mass. Just to even doing a flyby, especially if it's not a binary object, get you the mass to some extent. And so there's information you almost have to collect ahead of time if you can, but that's a huge luxury and a huge expense. So anyway, it's just something to think about.
Yeah, I mean, as you know, during these planetary defense conferences, there's a conference every 2 years where the community, and it's a pretty broad community that ranges from FEMA to climate modelers, impact hazard assessment people, and astronomers, and people that are discovering these objects. This meeting holds these scenarios, and we just finished one up a few weeks back where we have an impactor, and the question is asked, what do you do and how do you respond? And in most of these scenarios, having gone to several of these meetings now, a sort of reconnaissance probe is an essential part of the process, where ideally we'd have something like that on the shelf ready to launch, so that if something dangerous with a non-zero impact probability is found, we would launch that probe to start that characterization right away. We don't have a probe like that ready to launch. And the question remains, when would you launch? Do you wait for the impact probability to hit some threshold and then go, okay, well, let's quick do it now? Or, and these become political decisions. When agencies are willing to pull the trigger on doing that kind of, these launches are not cheap, right? And so it can be a tough decision about knowing when and how to act appropriately. But
yeah, so that's good to know.
So along those practical lines, the arc lengths of some of these things are very short when they're first discovered, and those are the ones that can be incredibly dangerous. So we have to get to where we think it is, and then we have to do the orbital maneuvers to get to where it is. In terms of practically carrying the fuel to make those maneuvers, is this something that is feasible?
I suspect the answer is, you could come up with, I think you can come up with any answer you want, depending on the details of the object, when it's going to impact, how big it is, what the orbit uncertainties are, and things like that. you're right. A lot of these objects, and I track the objects that JPL highlights as potential impactors. And we get alerts all the time of here's an object with a non-zero impact probability, follow it. And so people in the community follow those objects and make sure that that impact probability goes to zero, which in most cases is what happens. But there are, the few objects that are found that actually do impact us. Unfortunately, those tend to be pretty small objects. But yeah, I think anything's possible when you start talking about the details of the scenario, how much fuel you would need, how much delta V you would need to meet up with the object and things like that. Space is big and a lot of possibilities are out there. So I'm not sure there's a single answer that would apply to all this. We understand at least what the population looks like based on the objects we've discovered. And we think we understand what the underlying population is to, again, order of magnitude. So we kind of know the realm of parameter space we need to operate in any rendezvous or intercept mission. But each object is going to be different, and I'm sure there will be wrinkles thrown in if we ever have to do this for real.
Well, Nick, I think you've more than earned your non-existent honorarium for this. And thank you so much. What a wonderfully interesting presentation and experiment. I wish we could help out as amateurs, but we can't. Our little toy telescopes are just not big enough, are they?
Well, it'll be a fun show to watch, and that's by itself. Just watching how this thing evolves, I think it'll be really cool. And I don't know where I'm going to be for impact. Impact may, and there's some wiggle room at exactly when impact happens, and that translates to where the object will be overhead when it happens. But it may be overhead around Africa is kind of what we're looking at. So the object will be rising in Arizona a few hours after impact. And so it should still be evolving and maybe even brightening as it does. So it could be an interesting show, and it's going to take a little while for that ejecta to evolve to actually be resolved from the ground. So you'll see a brightening peak, and then eventually the ejector will evolve outwards until it actually can be resolved as a cloud. And so it'll be a fun show to watch.
Yeah. Oh,
and it'll evolve quickly, right? That's the thing is, the main brightening that will happen is over a few hours, and then the fading will take days, weeks, months. But it'll be fun to see. So I think we'll certainly try to get the Lowell telescopes for the smaller public program telescopes tuned in on Didymos when this happens, because it'll be hopefully a good show.
Good. Look forward to it.
All right. Well, thank you all for.
Thank you.
Thank you.
Tonight. Yeah.
And when are you coming back home?
Mid-July.
Okay.
So 2 months.
2 months.
Yeah.
Well, enjoy the rest of your trip and visit and relatives and all of that. Thanks again.
Very much. Yeah. Take care, all.
Bye-bye.
Good night.
Bye.
Okay, we got anything else to say here, or should we just shut down? Just over 2 hours.
Yeah,
Yeah.
I think we should